Good morning, everyone. Welcome all to EasyPower Thursday Technical Webinar Series. My name is Jim Chastain. I'm an applications engineer here at EasyPower, and today's topic of specifying the appropriate short circuit rating based on utility service is a highly anticipated topic. And I was telling Andrew that this is one of the questions that most new system modelers have to wrestle with on their first project. So we're expecting some good feedback from the webinar. And as we are in the habit of doing, we like to start each session before I introduce the guest speaker with a series of poll questions. And these I'm personally very interested in the response. There's no liability or obligation. It's strictly trying to get a measure of the audience's participation. So how often do you request utility fault current letters in a project? So if you would respond with your opinion or what is appropriate for you. A few housekeeping notes. There will be attendance certificates sent out via email probably towards the beginning of next week. So you don't have to do anything if you're a registered attendee today. Okay, so it looks like we're close to a quorum. Here's how folks have weighed in on this one. Okay, that's pretty heavily weighted. Good. The next question is, what tools do you use to perform short circuit calculations? And again, I appreciate your attendance today and participating. This is good feedback for Andrew to be able to amplify certain portions of his presentation. All right, let's give this another 5 seconds. Excellent. Here's how folks have weighed in on this one. Not that surprising since this is an EasyPower webinar, but I appreciate the fact that people use the software. All right. And the third question, what is the most common service entrance interrupting rating you specify when utility fault circuit current is unknown? This is a really tricky one, or an interesting one, I guess is more the appropriate term. So we're about 50% to a quorum. We're expecting a large audience today, so for those of you that haven't attended or don't know, we will be posting the recorded video of the webinar on the website. You'll receive a notice of the link to it. And Andrew has graciously agreed to also make available a copy of his slides that can be downloaded in PDF form. All right, so it looks like we have a quorum here. Interesting, at least for me. Excellent. And then finally, how often do you specify series rated versus fully rated equipment? This one's a little bit of a crossover topic, and it's intertwined with this topic today, so I'll be curious not only the responses, but how Andrew expands upon the possibilities. All right. Looks like we have a quorum. Here's how folks have weighed in. Excellent. Well, with that, I'd like to hand the baton over to Andrew Legro, an FAE with ABB. Andrew, give me just a second and I'll...
Okay, thanks, Jim. Let's see here. I'll make sure it's working. Can you see my screen?
I can, yes.
Okay, I'm gonna go to the presentation mode and make it full screen here. Okay, is it on presentation mode?
Yes, looks good.
Excellent. Thanks, Jim. Great kickoff. So yeah, hello everybody. Good morning or afternoon, depending on where you are. My name's Andrew Legro. I work for ABB as a field application engineer in Florida. I've also worked as a consulting engineer for about 8 years locally, doing some commercial and mostly healthcare type projects. So I've been on both sides of the fence, the manufacturer and the consulting engineer. So it gives me a kind of a good perspective. I've done a couple of these with EasyPower over the years, and I really appreciate the opportunity to share some of this info. Just some title stuff. For those of you that aren't familiar, and it could be a lot, ABB was General Electric. So I was a GE employee, and they acquired us 4 or 5 years ago. We still sell some stuff under the GE brand, but most of it's being converted over to ABB. So keep in the back of your mind, the ABB and GE are the same animal now. Little disclaimer, this could be some, hot information, I think, interesting to me, and could be controversial. So I wanted to put a disclaimer in there that this information that I'm going to present is not the opinion and recommendation of ABB in any official way. It's more or less my experience and information I've collected and best practices. So it's as is, and I'm sure there'll be people that have different opinions and whatnot, but it's sort of the best practices I could come up with, based on what my experience level is. So with that, let's move on. The whole purpose of this presentation is to help the consulting engineer figure out what to rate his equipment in terms of short circuit rating from the very beginning of a project. So you may not have a lot of information, and you never do. You got to start drawing stuff. And so what I tried to gear this towards is, okay, you got a basic concept of what you have to do. What steps can you go through to at least get in the ballpark of the correct interrupting rating of your equipment? And the reasoning behind it is that this kind of steps over here. Let's see. This in red. If something's in red, it's usually important. So that's sort of the going forward. That's what it'll be. It's important to determine the available short circuit early in the design phase of the project. That's because you have a limited amount of time, and when typically you would go request that fault current information from the electric utility, but usually that takes a lot of time because you have to find the right person has to be assigned from the utility, and then you have to go through a whole bunch of information submittals, and it can eat into a tremendous amount of time that you could use designing the system and optimizing it. So going to go through a couple more of these points here. Yeah, the type and cost of the distribution equipment, it's greatly affected by both the size of the service and the magnitude of the short circuit current available. It's not linear, so super high interrupt rating equipment is a lot more expensive than something that would be off the shelf standard. Next point is utility transformer size is by far the dominant factor in establishing the available short circuit current. So you need to know what size that utility transformer is going to be, then which flows into the next step. The engineer, he calculates the size of the service, but they have no control over what size transformer the utility is going to supply. That's the big unknown, and that's what sets a lot of the design parameters. And finally, the best, obviously, and eventually required method to determine the available short circuit is to get a fault current letter from the utility. And running into what I said a few seconds ago, this can be a very time-consuming process. And why delay your design process when it's something that you can ballpark or estimate intelligently and get pretty close. So the engineer has, I kind of boiled it down. The engineer has three options. You can wait for the utility to issue the fault current letter, and essentially hold off on doing your specifications. Two, overestimate the fault current and specify either expensive equipment or impractical equipment, equipment that's rare, hard to get, doesn't exist. Or three, the point I'm trying to get across, is use information at hand to try to accurately estimate, ballpark, the available short circuit. So this presentation will discuss the methods to estimate the available short circuit prior to receiving the fault current letter. And let's get into it. There we go, next slide. Here's the basic strategy. Think like a utility. The utility mindset. Utilities are very structured. They do everything by their internal pre-written handbooks / cookbooks. Kind of choose from column A, column B, column C. So they typically won't surprise you. So if you observe what they do, then you have a leg up on what you're probably going to get. So I put this in there. Their philosophy is the engineer once, use often, and that makes a lot of sense. I mean, for their objectives, they don't want to have any kind of new designs for every service or every substation. They like to do cookie cutter stuff because they have to keep the cost down. They have to build it quickly, and they have to be able to maintain it. So they have a big job to do. So consistency is their whole ball of wax. They really drive towards consistency. So here's some points. The design of the utility distribution feeders is usually consistent and won't exceed a certain maximum fault current level. The utility designs its distribution feeders based on X amount of fault current, period. And that's when they give you the fault current letter, that's what they're giving you is their design, not what's actually there, but their design maximum. And we'll get into that a little bit more. The transformer specifications, basically what transformers a utility can select from, they're consistent. They're defined in IEEE C57 standards, so there's only a certain amount of ratings and there's only a certain amount of impedances based on those ratings. So they have a very limited toolbox of the physical equipment they can supply to power your project. So that you can really work to your advantage. And we'll also get into that too. And I think I kind of a repeat there. Transformer kVA ratings and impedances are standardized. Just kind of reiterating, there's not that many of them, and we'll get into a chart showing all of them. tips for the engineer. It's useful if you're going to do a project with a new utility or even a utility you used before. I like to go and Google something like the utility name and then electric service standards, or utility name construction guidelines, because there's typically, every utility has a handbook of electrical service requirements and or construction standards. And it can be it can vary in size, but there's always good information in there, and that tells you all the little tricks that you have to make sure that you comply with to be able to connect to that utility. So there's always a lot of really good information though. So I suggest any project, once you determine what the utility is, that service is, that project is going to be, do a little search on the internet. Then this is helpful too. If you're local to the project, drive around the site and just see if you can figure out how neighboring buildings are being served. If there's a single distribution feeder, just kind of do a lay of the land thing, and look at other people's services. Look at some existing pad mount transformers. Sometimes you can get lucky. Often they only put sort of arbitrary, serial tag numbers and indecipherable stuff in block letters on the outside of the transformer, because most of the time the nameplate is on the inside door of the transformer, so you can't see it. Sometimes you get lucky and people are putting the nameplates on the outside, and then you can get all the primary voltage and the transformer size, the impedance, all that great information. So it's good to go out and take a look at the general area that the project's going to be in, and then develop some contacts at the utility, especially if you're work in a certain region. Try to develop some decent contacts. They'll give you some hints on how they do stuff. And then whenever you do get fault current letters, just keep them in a file so you can reference them again, because they're always usually you can end up being in a project that's very similar and get the same answer. Just a really quick thing. This is actually pretty close to my house. I like this area because it shows a lot of stuff going on that explains kind of how utilities work. So most importantly to us, this is the distribution circuit. And usually the distribution that's feeding your, the primaries of your transformers is limited to a 15 kV or sometimes a 23 kV service up to 25 kV. Occasionally you get a little bit higher, but probably 90% is in the under 23 kV range, and it's going to look kind of like this. And part of it's more than likely going to be overhead, especially if you're in a suburban type area, not high density. And then when it transfers to underground, this is what it's doing here, essentially goes from an overhead line, connects up with some fuse cutouts, goes underground. And then this is nice so you can compare it to what the utilities kind of refer to as sub-transmission. And these are the circuits that go from substation to substation. They're not really long-haul transmission, but they're there to interconnect local substations together. But most of the time, 99% of the time, the customers are not drawing power directly off of a sub-transmission circuit. There's a couple of rare instances. If you're a big industrial, you may be able to get connection to a 69 kV circuit. And I've seen it. They pay big money for it. They're very reliable. They're very stiff. But it's not rarely done. So most are going to be on distribution level. And then you can kind of see in the background there's a transmission line. It's I believe it's 138 kV. So it's kind of a nice picture. Shows it all together. Okay, so here's the scope of the presentation. This really applies only to radial distribution with a single transformer. So the good news is that at least in my world in Florida, that covers about 98% of all the services. So in other words, you have a radial distribution feeder coming out of a substation. It serves a street. There may be a couple lateral taps off of it, and then it drops into a transformer. No networking, no network connections on the primary or secondary. It's just a source and a transformer. And most of the work that I do in Florida, and anything really that's not going to be in a high density urban environment, will be covered under this radial system. You can see here exceptions. I'm accepting network type distribution, which you usually get in dense urban, especially in New York, like Con Ed, Manhattan, high density areas in New York uses a lot of network distribution, and that's a totally different animal. You can get some very high fault currents on those systems. So this presentation does not cover that. It's another topic entirely. In scope, basic services, 3-phase, low voltage, 12208 and 48277. Customers, light industrial, commercial, institutional, multifamily residential, office buildings, kind of the bread and butter of what consulting engineers do that do commercial projects. I mean, everything except for basically customers with big motors. So heavy industrials out, but probably 80-90% of the projects that get done this covers. Pad mount or vault style 3-phase transformers. This is kind of what we're focusing on. Pole mount transformers. There's not going to be much difference, but I didn't include any information on those. So this would apply to pole tops too. You just have to be careful about the impedance and make sure you have a chart for those, because those can actually have fairly low impedances to them. So you can get surprised by a pole top. And here in scope, no parallel generators or closed transition switching, standby fine. But no, single standby is fine, but no big paralleled or cogeneration, stuff like that. So now you see exceptions, cogeneration, obviously. Single phase and odd voltages didn't cover. Single family residential is a different animal. That's pretty consistent as being the 10K interrupting. Large industrials, medium voltage, no discussion of medium voltage as the service. We discussed it on the primary, the transformer, but not customers served by medium voltage. Pole tops, and then the big one is network type distribution isn't covered. But the conclusion of this is that most of the stuff that the bulk of consulting engineers deal with is actually falls in within the scope. So this is just trying to state the point that the fault current that you're going to get at your project is essentially the sum of 3 separate impedances. You got your utility distribution feeder, and it's got impedance to it, and it can range between 2 and 20. 20 is really high. Usually it's going to be more closer to the lower end. And these impedances are relative to the total. So 20% of the total source impedance may be from the distribution feeder. The utility transformer, I have this highlighted in red, because this is trying to convey that the utility transformer is where you're going to get the bulk of your impedance. And so this is the critical component that's going to set that fault current. Then you have service entrance conductors. Those are your cables from the transformer secondary to the building. Those really don't add that much unless you have a really long secondary run. But if you're in the range of 50 to 100 feet of secondary, and you're bringing the full transformer ramps out, it's not a huge number. So this really, the point of this slide is to convey that it's this utility transformer that you have to know. That's the important one. We have to know the impedance. This slide, I tried to summarize essentially the whole presentation in a series of steps that the engineer would take when he's trying to make that determination of how big do I specify my switchboard interrupting rating, or panel interrupting rating, or switchgear. So step one, research utility and project location. We kind of covered this. Be on the lookout for radial versus network systems. What the distribution voltage is. Pad mount versus pole top services, and then try to search out any existing transformers on the project site. Then step 2 is start the project design and calculate the project demand load the normal way that you do it per NEC. And I got some helpful hints here. Generally, I like to limit individual services to 4,000 amps or lower, because the equipment gets rarer above 4,000 amps. I mean, we make it, other people manufacture it, but it gets very expensive, very unruly. And usually, if you have a building that requires more than a 4,000 amp service, the AHJ will let you establish essentially, multiple services for the building because of the size. So I try to limit an individual service to 4,000 amps or lower, because that keeps you in conventional type equipment. Make sure you include some growth capacity, and note large motors, including the starting method like cross the line or soft starters or VFDs, because the utility is usually always very interested in the motors, because that's how the motors are motor starting is one of the things that utility does use to calculate its service and the size of those transformers. Step 3 is a big one. Once you got that demand for the building calculated out, then this is where you want to try to estimate the transformer that the utility is going to provide. So here's my rule of thumb, and this could be controversial, but I've had pretty good luck with this. You take your NEC demand and cut it in half, and that'll be probably the largest kVA transformer that the utility will provide. And I'll get into an example with this. Step 4, using the I'll get into this. Using the estimated short circuit on the utility feeder plus the transformer size. So all the information basically in step 4, construct that short circuit model in EasyPower. So this is at this point you have all the information that you need to start running calculations. And then step 5, it's simple. Just get whatever the result of your calculations are. Specify an interrupting rating, obviously larger than the available short circuit current, and in line with standard equipment types. Because it can vary. If it's a switchboard, getting up to 100 kA isn't really that difficult. It's available. If you just have a service that just has like 40 volt lighting panels, that's going to limit you. So you have to be cognizant of the standard interrupting ratings and also the equipment type that you're going to have serving your load. And then finally, after you get to your step 5, remember to verify calculations with the electric utility fault current letter. Hopefully by this point in the design process, the utility will have time to come up with that. So, you ask for it in the beginning of the project. It takes a long time usually to process through. So by the end of the project, when you're about to release, bid documents or construction documents, you should have that letter. And hopefully what you come up with is going to be conservative high over what the utility is actually going to provide you, but in the ballpark. Here's kind of a key thing. This is talking about the impedance of the primary that feeds the transformer. This is the impedance of the utility's distribution feeder. From talking to utility engineers and just due to experience, essentially this kind of applies to most of the utilities down in Florida, but it really is kind of a consistent thing. Because utilities design their distribution feeders to basically be a certain size, and that's it. They don't have a bunch of different sizes and fault currents. So anyway, their design point for a typical either 13.2 kA or 22, so it doesn't matter what the voltage is. Their design point in terms of fault current is 6.7 kA. That's it. That's what they're designed to. And the reason is the distribution equipment, like fuse cutouts, things that are on that overhead line, they're really only limited to about 10 kA. It says it right here, rule of thumb, no more than 10 kA available for medium voltage utility distribution feeder, regardless of voltage. So, and there's sometimes it ranges from 8 to maybe 16 kA, but it's really no higher than 16. So 10 kA is a good number, and that sets the limit. So, yeah, a couple specific utilities that I work with, they design their feeder for realistically 6.7 kA, no more. But then they tie in, they create a worst case maximum because they say, okay, there may be some cogeneration on that line or renewables and things like that. So I want to bump up that number, get a little bit conservative to account for the contribution of those customers. So they take 6.7 and they bump it up to 8.3 kA. And when they do their calculations for their utility fault current, they use the higher number. They use the 8.3, even though it's arbitrarily high. So this is the first level of where you see padding and conservative numbers being put into fault current calculations. But it's still a nice number because it's relatively small. So 8.3 kA is not very high. So that will choke off the fault current in your transformer. So this is the first key. Is now we know what the impedance and the available fault current of the source is going to be. The source to the utility transformer. So here's a little bit about that 50% rule of thumb I was talking about. The breakdown is that engineers, they have to obviously determine the service size based on NEC, and that's a high number, and it's high for a couple of reasons. One of which is that when you say a 2,000 amp main breaker, they can only take 2,000 amps for a few seconds. There's no overload on that. It's just it's either less than 2,000 or above 2,000. But the utility system, its equipment, particularly the transformers, they have a very long time constant. You can really overload transformers. So really the concept of the service entrance protective equipment versus what the utility is supplying in the transformer, they're not the same thing. So you got to keep that in mind. So yeah, obviously engineers have to apply NEC. And then electric utilities, they're not required to follow the NEC. And when they do their sizing calculations for the loads, they don't really use any NEC stuff at all. They do a couple different methods. Most typically, they do a kind of a watts per square foot takeoff. So if it's an office building and it's X amount of square feet, they'll use a number like 7 watts per square foot or something like that. Done. Because they have a lot of data from basically all the customers that are on their system, so they got a really good idea of what the real demand is going to be on the buildings. So they usually do that. That's kind of how they do their takeoffs, or the watts per square foot method. There's some other ways they do it, but generally it's based on the type of occupancy, their tables of watts per square foot, and then motors. That's where they are interested in the largest motor. So usually when you fill out a utility application for a new service, you got to list the big motors you got, because those are the wild cards, because those don't get accounted for in their watts per square foot table. Big point is that, skipped one here. The big point is that the difference between the NEC calculated service and the utility's transformer size that they're going to provide can be substantial, really big. So that comes into the rule of thumb. To estimate the size of the utility transformer, take your NEC service and take 50, cut it in half. and round up to the next transformer size. And 9 times out of 10, you're still going to be higher than the transformer they're going to really provide. Here's an example calculation. So you have a building, and you calculated the service to be 750 kVA, and it's going to be served at 480 volt. So you, as the engineer, you say, okay, I'm going to specify a 1200 amp main switchboard, and that'll give me a little bit of extra capacity, because 750 at 480 is only 902 amps. So I bumped it up a little bit. I got a 1200 amp service. So now I'm going to take that number, 750, my NEC calculation, cut it in half, 375. I'm going to say, okay, 375 is what the utility thinks they have to supply. So now I'm going to round that up to the next standard size transformer, that's 500. So now you can be fairly certain that the utility will provide no larger than a 500 kVA transformer for your 750 kVA service. Realistically, and in the same situation, it's probably going to be a 225 or 300. So you still have your conservative, you're still high, conservative, but you've dropped it down from 750 to a 500 kVA transformer. So that's the maximum that you could really expect the utility to provide. And that's only, if you notice, that's only 600 amps. So you got a 1200 amp switchboard, 1200 amp worth of cable feeding that switchboard off a 500 kVA transformer that can only nameplate produce 600 amps. Now this is kind of a discussion on why, and I've already broached this a little bit. The transformers have a lot of thermal mass to them. They're a big hunk of steel, copper, but then with the liquid fills, more importantly, they have a lot of oil in them. So here's a statement. Compared to dry type transformers, liquid filled transformers have a much longer thermal time constant due to the additional oil mass. So it takes a long time. You can overload these for a long period of time before you get them hot. Overloaded transformers don't immediately fail. They just age faster. So the more hours you put in an overloaded transformer and the hotter they get, their lifespan goes down. They don't immediately fail, and their lifespan's about 20 years. And there's some really good IEEE standards on actually estimating, you know, I'm going to overload a transformer by this many hours per day, what the lifespan reduction is going to be. There's a lot of work been done on that. That leads me to a point here. You know, decades of research and analysis on transformer loading has yielded very accurate guidelines for loading versus lifespan. So bottom line is utilities don't want to spend a lot of money that they don't have to. So they're going to give you the smallest transformer in terms of kVA that will practically work on a system that you designed. So that's the difference. But it's all real. They're not. No one's shortchanging you. It all works out because it's all based in a long period of operation and their knowledge base. So I constructed a table of the standard transformer sizes, and these are defined in IEEE C57. C57 is the 57 part is the transformer set of standards. So it'll have a number like C57, and this one is .12.00 is liquid filled transformers. Anyway, there's standard sizes defined by IEEE and the manufacturers comply with. You can get one built that's not this standard, but utilities don't. So if this is for 208, 120 208 volt services. So if you're looking for a 120 208 volt service, this is the options. That's it. And notice you max out at 1500, and even that's high. a lot of utilities won't put out 1500 kVA 208 volt transformers. They'll top off at 1000, but no bigger, because it just they don't make sense. They economically don't make sense. From a stocking and operations point, they don't make sense. So for 208 volt, 1500, biggest we're reasonably going to get. Then I got the percent impedance, and this is kind of either low or average percent impedance based on C57. So you can tell the smaller the kVA, the lower the impedance is going to be. Then I calculated full load amps, and then I put together and added this to it, infinite bus. So this is if the utility's primary has zero impedance, and you're just looking at the transformer impedance, how much fault current are you going to get? So that's the infinite bus number. And then I used the primary, where the primary utility, utility on the primary side has impedance, and I'm using that 88.3 Ka number. And I actually did this in EasyPower. And I ran the examples to show, okay, now I have that 8.3 Ka available, then goes through the transformer, and what do I get? So you see, and this is what I found very interesting. It's lower than the infinite bus, but not much in the smaller kVA size transformers. For example, if it's a 75 kVA infinite bus, you'd get 7.7 Ka of fault. And then when you do the calculation, including the impedance, 7.6, not a big change. Then when you get into some of the bigger units, 1500 kVA, it's 72 Ka infinite bus versus 63 Ka with including the source impedance. I did the same thing for 480 volt, 277, and you can use these tables when you do, these calculations that you're doing. This is pretty good reference, because everything except the last column is using the 83. I've got it noted, star, calculated using 13.2 kV source with 8400 available fault current. So, but everything prior to this is directly out of C57. So this is all real information, not just something I invented. So you can use those tables. Now I ran through an example of a short circuit calculation. Beginning from a blank sheet of paper where you have to design the building. And it kind of runs off the same example we were talking about before. Calculated load, and you calculated an office building load of 750 kVA at 480 volt. You specify a 1200 amp main switchboard. You determine with the 50% rule of thumb method that the transformer size is going to be 375 rounded up. So you determine it's going to be a 500 kVA transformer. And then you estimate the utility, obviously, the utility you're estimating is going to provide 500 kVA. From the tables, if you go up here, the impedance of a 500 kVA transformer is 4.35%. Now that's actually low, but this is what's published in IEEE. I would use 5.5%. So this will give you even a more conservative number if you use this 4.35. So take it from the table, 4.35, and we're assuming the utility primary side can deliver 8.3 Ka at 13.2. So you put all this in EasyPower, you construct the circuit, got your utility, got your utility with its available short circuit, just 13.2. Then your transformer, a transformer with the right impedance. Then your low voltage side, bus right on the secondary of the transformer. And then I included 50 foot of cable sized out for 1200 amps. So by the time you make it to the service entrance on this system, you're at 12.7 Ka. Now think about it. That's a lot lower than what it ends up getting typically specified for a main switchboard on a office building, a main 1200 amp switchboard for an office building, you know, a lot of engineers will just default, okay, 65 KA. That's a big difference. So realistically, you're really at 12.7 KA, and this is a conservative calculation. So that's kind of a take-home point of this slide, and we'll continue with this. We continue with this example here. Okay, so you'll say, okay, that's great, but it's 12.7 KA, but you didn't include any contribution from the load, from the project site, and there could be some big motors there and whatnot. So I said, okay, let's continue the argument. So I added a 200 horsepower induction motor, cross the line start, directly on the service entrance bus. And that's 200 horsepower off a 500 kVA transformer. So that's pretty serious. That's probably pretty close to the biggest single motor load you want to put on a transformer that size. So okay, how's that going to change the short circuit? So in EasyPower, I just added the motor, same circuit up here basically, and now I came up with 13.9 KA. So I went from 12.7 KA to 13.9 KA, about 10% increase. And it's a decent increase, but you're still in the same essential range of low-end interrupting rated equipment that you haven't really shot into a new category. Okay, then this here is, okay, let's argue that, well, you really don't know what that primary fault current is coming from the utility's distribution feeder. You're really just guessing at that. Okay, well, there's a way around that. You can say, well, I'm going to assume an infinite bus. And an infinite bus is essentially saying that the primary of that transformer can supply an infinite amount of fault current to it. There's zero impedance to it. And this is just some equivalent circuit showing an infinite bus. So basically, I zeroed out the utility, so I got the source. I zeroed out the utility distribution feeder impedance. A utility transformer is 100%. That's all the impedance going to be. And this will be a number that comes off that chart, 4.3 or 5.75. And I even zeroed out the cables on the secondary transformer. Absolute worst case. So you can do that if you want. If you're not sure about relying on what that primary is going to be, that primary short circuit, and you just want to be a little more conservative, do an infinite bus. And I did this this has surprised me a little bit. I plotted out, using EasyPower to do the calculations, I plotted out the difference between calculation based on infinite bus versus using the actual fault current, which I was assuming is the 8.4 KA at 13.2. So if you notice, in the small transformers, they're 45, all the way up to 500 kVA, there's only a 6% difference, which is very small. Now, once you get into larger size transformers, especially above 1,000, then it gets significant. So now, like for example, at the worst case, the 3750 kVA transformer, your infinite bus is going to be 134% larger than the answer you'd get assuming a source impedance, a realistic source impedance. So yeah, it's kind of an exponential curve. But if you're on that low end of the curve, it really doesn't make much difference. And even on the higher end of the curve, an additional 34% is not going to put you in a different category of KA rating. It may move you up a little bit, but it's not really that much. So this point in the presentation, I've said, okay, we figured out what the available fault current is. So now I'm moving on to the selection of the equipment. And I'll go through this really quick. The only two that I want to kind of review real quick is that you have two terminologies that's important. You have your available fault current. That's obviously what you calculate. That's the amount of fault current that's available at whatever bus. And then you have your interrupting rating, and that's for the circuit breakers, and that's the maximum amount of fault current that they can safely interrupt. And I'll speed through this a little bit, and if you're interested in more detail on these short circuit calculations and some of this more detailed information on what the short circuits actually look like in terms of the symmetrical and asymmetrical, that's an entirely different subject, and there's a lot of good resources on that. But the take home is that this is what you have to know. What you have available, and then the interrupting rating of the equipment. And you can read this on your own, some other stuff. So here's a little table I put together saying, okay, here's the standard interrupting ratings for low voltage equipment. What they cost, kind of in relative terms, and some notes on them. So you see 10 kA, that's standard for 240, 208 load centers. That's the minimum you're going to get is 10 kA. So if you go to Home Depot and you buy, a ADD load center, it's going to be 10 kA. For 480 volt lighting panels, kind of the default minimum is 14 kA. Now note that whole process we went through, we never really exceeded 14 kA. So in theory, that service could be applied to directly to a 40 volt off the shelf lighting panel, and it would still be fine. Then you get into some of the larger ratings, and largers, I got the kind of caveat, because if when you go into like a switchboard type construction, bigger than a lighting panel, so maybe switchboard, maybe power panel, your low end is going to be 35 kA. So 35 is kind of your standard for low interrupt switchboard type equipment. 42 would be medium, relatively low cost, maybe a little bump from 35, but relatively low cost. And then you get into, and I have this highlighted red, your 65. So that's what everybody picked. And I found it interesting, the poll question confirmed that. Everybody picked 65. But 65 is really high interrupt rating stuff, and you pay for it. It's more expensive than the same switchboard in 35 kA. And there's really no difference in technology. It's mostly a labeling exercise, but there's a significant cost bump. And not only cost is important, but also the availability. As you pick higher and higher interrupt rating devices, the equipment's not as readily available in stock. Different types of equipment, so you got to keep that in mind too. And then when you start to get really crazy, this is where 100 kA is where switchboards basically top out. That's very high interrupting ratings. You can get them. It's the same kind of switchboard that would be 65 or 35, just higher interrupt breakers. Very expensive. The cost goes up. And past 100, you get into some really weird situations. There's not a lot of equipment that can that you can select from that can do above 100 kA. This is at 480 volt. So it gets a little strange. It's hard to get. It really becomes an issue. But usually you don't hit these realistically until you're in a network type vault situation, and that's another topic entirely. A network system, primary, secondary network system. So there's back to our example. We're coming to a conclusion here. Pick a standard AIC value greater than the calculated available short circuit. Make sure it's appropriate for the equipment, such as being a panel or a switchboard or switchgear. Since our example that we were working with is a switchboard, we're going to select the lowest standard on a switchboard, 35 kA, typical low interrupt rating for switchboards. So now we specified 35 kA at this bus, which is only going to produce 14 kA. So we're well within. We have padding on top of padding on top of engineering service factor. So we have a lot of safety factor. So we have a lot of margin on that, and we're still in the basically a low end switchboard for this service. And then finally, kind of continue the example out logically. Okay, well, there's going to be some downstream panels on that. So I just added a panel board, 40 volt panel, and I assumed 200 amps, and I assumed, I think, 100 feet of cable, just to see if you can get away with a standard lighting panel without any problem. And yeah, you can. So standard 40 volt lighting panel is 14 kA. As you expand this short circuit calculation out, at this panel you get 10 kA of fault current. So you're perfectly fine doing a low end off the shelf 480 volt 14 kA panel. So your switchboard's 35, and then the stuff, ancillary panels downstream could be low end. That'll save you a lot of money. So I have in here, reduce project cost, and then avoid having to go with series rated equipment, because you could, in theory, have a lower rated panel, but then series rate it to the feeder, and that's definitely a solution, but it gets messy. And if you don't have to do it, then don't do it. And most cases you won't, because you're going to get much less fault current than you assume. So that's the end of the presentation. Hopefully it was helpful. I'm curious to get your feedback, because this is the first time I just put this together, so I've never presented before until today. So I'm interested to see if it met your expectations, or what your thoughts on it are. And then just a couple final thoughts. Always note that the short circuit information provided by the utility, it's intentionally conservative, biased on the high side, and its only use is for specifying equipment short circuit ratings. It's the only thing you should really use that number. So when you get the utility fault current letter, that number is used just to size your equipment short circuit interrupting rating. That's it. This brings me to the second point. Unless very careful verification is made, utility short circuit letters should not be used as a basis for other calculations, such as motor starting, voltage regulation, and harmonic analysis, as the conservative high nature that you're going to get is incompatible with calculations that require a conservative low assumption. So you're going in the wrong direction when you do calculations like motor starting and voltage regulation, harmonics. So that information is you need the worst case low for those kind of analysis, so it does not apply. So just be careful with using that short circuit information for stuff other than interrupting, short circuit specifying type calculations. So I appreciate your attention, and thanks to Jim and EasyPower for letting me do this. And I will I'll let you go. I think I'm pretty close to being time. If you got any questions, feel free to shoot them over. Here's my email address. So that's it. Thank you very much.
Thank you, Andrew. Yeah, the questions that were submitted will respond via email. Thank you.